Assalamualaikum to Dr. Saratu Iza binti Samsudin. My name is Nur Fatihah binti Muhammad Sabri and my group members is Nur Iza Izati binti Muhammad Zaini, Emilia Ashikin binti Azrani and Nur Shazwana binti Anwar. Today we want to present about group assignment.
Hi, my name is Emilia Ashikin binti Azrani and my matric number is P122310011. For this assignment, we were required to design a control system based on a given electrical setup. We had to apply the theoretical concept we've learned in class, such as a system modeling, controller development, and stability assessment in order to complete the project. To support our design, we use MATLAB for simulation. This helps us analyze the system's performance and validate whether our control design worked as intended. Overall, this project allowed us to connect classroom theory to real-world application. It gave us hands-on experience in designing and evaluating a control system. Lastly, this assignment also helped us to improve our communication skills, especially in writing technical reports and giving presentations. For objectives, apply theory in system modeling, controller design and stability analysis. Design and analyze a control system from an electrical circuit. Derive the system's transfer function. Design a controller with 5% until 25% overshoot. For our assignment, we choose 15% overshoot. Evaluate stability using Rother-Weights. Simulate system response using MATLAB. Verify design through step and frequency response.
Hi, Assalamualaikum. My name is Nur Izazati. My matric number is B122310554. And now we present part A, system modeling. System modeling form the foundation of control system designed by providing a mathematical description of physical system. This means we start by converting the real electrical circuit into a mathematical model that we can analyze and simulate. This process allows engineers to predict system response, evaluate dynamic characteristics, and design suitable controllers. By modeling the system accurately, we can predict how it behaves and make sure our controller will work properly. In this project, both time domains, state space, and frequency domain transfer function modeling approach were applied to represent the electrical circuit. We used two methods, which is state space and transfer function, to fully capture the system behavior. The key is to understand how the system reacts to input variation, analyze its stability, and prepare it for effective controller design. This helps us know if the system is stable and ready to be controlled according to our specification. The result was simulate and compare using MATLAB to ensure the design is both theoretically sound and practically applicable. Finally, we use MATLAB to simulate and compare the models, making sure our theoretical work match the actual system performance.
For question A, frequency domain. Derive the transfer function of the system in frequency domain. So this is our circuit electrical system. At the circuit, there is two resistors with value 2 ohms, one inductor with value 2 Henry, and one capacitor with value 2 farad. For this part, we need to find G equal to V out per V in. There is two loops. For loop 1, I1 R1 plus I1 R2 minus by I2 R1 equal to V in. And the equation for loop 1 is 4I1 minus by 2I2 equal to V in. For loop 2, I2 R2 plus I2L plus I2C minus I1 R2 equal to V out, and the equation for loop 2 is I2 2 plus 2S plus 1 per 2S minus by I1 2 equal to V out. Next, in this calculation, we are solving for the current I2S using metric methods from a system of equation in the Laplace domain. We begin to put the equation of loop 1 and loop 2 into the metric equation. To find I2S, we use Cramer's rule. We replace the second column of the coefficient matrix with the input vector and compute the determinant. The numerator becomes equal to 2 and the denominator is the determinant of the original matrix. This implies 2v in per x plus xs plus 2 per s minus 4. Finally, we simplify and obtain I2 equal to 2v in per xs plus 2 per s plus 4. Then we express this as a rational transfer functions in terms of s. I2 equal to 2s v in per xs squared plus 2 plus 4s. So the output over input voltage becomes V out per V in equal to 2s per xs squared plus 4s plus 2. And by factoring of simplifying, we get the final transfer function. V out per V in equal to 1 per xs squared plus 4s plus 2. This transfer function represents the behavior of the system in the S domain. In this part, we analyze the unit step response of the system using MATLAB. The transfer function we use is 1 per xs squared plus 4s plus. We wrote a simple MATLAB code where we define the numerator as 1 and the denominator as x for 2. Using the step function, we plot the system's step response. The result waveform shows how the system behaves over time when subjected to a unit step input. From the graph, we can see that the system has a small overshoot and eventually settles at a steady state value, indicating it is stable and under damped. Next, we need to identify the poles and zeros of the system using MATLAB. From the code, we use the poles SYS and zeros SYS commands. The output shows that the system has two complex poles at negative 0.2500 plus minus 0.4330 imaginary, and no zeros as indicated by the empty vector. This means the system is second order and under damped, which is consistent with the slight overshoot and oscillation observed in the step response.
Next is state space. We convert the transfer function of the system in A, which is electrical system circuit, to state space representation. This is how we convert it. Cs over Rs equal to 1 over xs squared plus 4s plus 2. As shown in handwriting working, we derive the state space metric and substitute them into the formula. Gs equal to C times open bracket Si minus A close bracket inverse time B. The result shows the unit state response of the system, where we can clearly see the overshoot and settling behavior. Next, we simulate the unit state response using the state space method in MATLAB. First, we define our metric A, B, C, and D based on the values we calculated earlier. You can see the code at the top left. We use the SS2TF function to convert state space into a transfer function and then simulate the response. In the result section, we got the transfer function as 0.125 over S squared plus 0.5s plus 0.25, which match our earlier model. So this confirms that our state space and transfer function are consistent. Next, we look at the graph on the right. This is the unit state step response. We can see there is a bit of overshoot, but the system stabilizes after a while. This shows the system is under damped but still stable, and the response is what we expected from a second order system. So overall, this simulation helped us confirm that our state space model is correct and reflects the system's actual behavior. Next is observation based on both transfer function and state space representation modeling. Transfer function observation, it involves expressing the system as a ratio of the output to the input in the Laplace domain, assuming initial conditions are zero. In this assignment, the two-loop RLC circuit was analyzed using mesh analysis and Cramer rule to derive GS equal to 1 over 8s squared plus 4s plus 2. We observed that the pole and zero are easily recognizable, and it can be helpful for frequency domain analysis such as Bode and Nyquist graph and for calculating steady state gain. Next, students can use the poles to assess stability, and in this case the denominator shows a second order stable system complex pole. Next, we observe that this form is more flexible for systems with many inputs and outputs, or for implementing modern control methods into practice. This means we can easily use state space modeling in more complex systems compared to transfer function. Next is simpler and more precise time domain simulation includes step or impulse response, especially when done numerically in MATLAB. With this method, we can simulate the system behavior more accurately using tools like MATLAB. Next is easier modeling of internal system. Dynamic may be directly accessed and analyzed compared to the transfer function. In state space, we can observe how the internal part of the system behave, not just in input and output. Then, analysis of controllability and observability, which are important in modern control theory. These two properties help us decide if we can fully control or observe the system, which is important when designing advanced controller. Next, we compare the simulation result with theoretical approach. The comparison between the theoretical analysis and MATLAB simulation confirms that the system model accurately represents the electrical circuit behavior. The transfer function derived GS equal to 1 over 8s squared plus 4s plus 2 was obtained through both mathematical modeling and circuit analysis. Key performance characteristics such as system stability, damping nature, and step response behavior was consistent between the theoretical calculation and simulation outputs. The shape and response time of the MATLAB step response closely matched the predict behavior from the transfer function analysis. This consistency demonstrates that the modeling process was correct and that MATLAB effectively validates the theoretical system design.
Next, this slide explains the purpose of our controller design. The main goal is to modify the system behavior so it meets certain performance criteria like response time, stability, and overshoot. In this project, we use the controller as a gain compensator, meaning we adjust the gain value K to control how much the system overshoot. Our target was around 50% overshoot. This is within the acceptable range of 5% to 25%, and it's chosen to make our project result unique from other group. Next, this slide shows the detailing calculation involved in designing our controller. First, we determine the desired system specifications such as the target overshoot and settling time. Using this, we calculate the damping ratio and natural frequency. Then, we use this parameter to design our compensator, specifically adjusting the gain value K to meet the performance criteria. These calculations are essential to ensure the system responds as intended with improved stability and within the target overshoot range. Next, this slide shows the MATLAB simulation and transfer function setup used in our controller design process. On the top left, you can see the MATLAB code where we find the transfer function using ZPK command, which represent the system in terms of its zero, pole, and gain. We then plot the Bode diagram to analyze the frequency response and stability margin of the system. On the top right, we use the transfer function in zero, pole, gain form. The simplified the system model. It shows the system mathematical representation, which is essential in understanding its behavior. At the bottom, we include manual calculation for voltage gain. The gain in decibel was converted to the linear ratio, and final transfer function was derived step by step. This helps us validate the MATLAB result with hand calculation and ensure accuracy. Next, this slide shows the board diagram of the system, which include both the magnitude and phase plot. From the graph, we can observe two important stability margin. First, the gain margin is 24.9 dB at the frequency of the 2.29 radians per second. The second is the phase margin is 70.8 degrees at the frequency of 0.576 radians per second. This value indicates the system has a good level of stability. A positive gain and phase margin means the system can tolerate some increase in gain or delay without becoming unstable. At the frequency of 0.684 radian per second, the magnitude is about negative 2.66 dB, and the phase is approximately negative 1 to 6 degrees. This board plot helps to understand how the system responds to different frequency and give us instinct into how stable the system in its current configuration. Next, this slide explains how the controller design improved the system performance. A gain compensator was used to meet target overshoot requirement of 50% by carefully adjusting the gain value. The system showed the better response with less overshoot and faster settling time. The simulation done in MATLAB confirmed the controller made the desired performance. This highlights how important the gain tuning is in shaping how the system behaves. Overall, this part of the project shows how both theoretical understanding and simulation tools can be used together to get the best value within the given system requirements.
Hi, my name is Nur Shazwana binti Anwar. My metric number is B122310502. Today, I would like to present about part C, which is stability analysis. Stability analysis is an important part of control system design since it determines whether the system will respond to inputs or disturbances predictably. To operate safely and reliably, its output must stay restricted throughout time, which is ensured by a stable system. Despite evaluated system stability using analytical and simulation-based techniques. To ascertain the stability characteristic of the proposed system, techniques such as a Hurwitz criterion, pole zero analysis, and evaluation of the time domain response are used. By applying these methods, students are able to predict system behavior and implement necessary adjustments to ensure the system meets safety and performance requirements. Next, investigate and provide the stability analysis of the system with Hurwitz method. Hurwitz analysis. Student was used block diagram shown below, which was derived from the transfer function in part B, which is controller design. So in the block diagram closed loop, the numerator is 4.08 and the denominator is 8s to the power of 3 plus 84s to the power of 2 plus 42s plus 20. Because it is closed loop form, student must calculate the TS to find new transfer function using closed loop formula. GS 4.08 divide bracket S plus 10 bracket 8S square plus 4S plus 2 equal 4.08 8s cubed plus 4s square plus 2s plus 8ds square plus 40s plus 20. So equal 4.08 divide 8s cubed plus 84s square plus 42s plus 20. Closed loop formula is Ts equal Gs divide 1 plus Gs Hs. So enter the value 4.08 divide 8s cube plus 84s square plus 42s plus 20 divide 1 plus 4.08 divide 8s cube plus 84s square plus 42s plus 20 bracket 1 equal 4.08 divide 8s cube plus 84s square plus 42s plus 20 divide x xs cube plus 84s square plus 42s plus 20 divide xs cube plus 84 square plus 42s plus 20 plus 4.08 divide 8s cube plus 84s square plus 42s plus 20 equal 4.08 divide 8s cube plus 84s square plus 42s plus 20 divide 8s cube plus 84s square plus 42s plus 20 plus 24.08 divide 8s cube plus 84s square plus 42s plus 20. So the final answer is 4.08 divide 8s cube plus 84s square plus 42s plus 24.08. Therefore, the new transfer function is as shown in the figure below. So the new block diagram, the numerator is 4.08 and the denominator is 8s cubed plus 84s square plus 42s plus 24.08. Stability analysis is generally performed on the system's characteristic equation, which is derived from the denominator of the transfer function as it indicates the location of the system poles. 8s cubed plus 84s square plus 42s plus 24.08. This is already a third-order polynomial, and students directly apply the Routh-Hurwitz criterion to it. So this is the calculation of Routh-Hurwitz. S cubed 8, S square 84, S to the power of 1. The answer is 39.70. S to the power of 0. The answer is 24.08. Next, S cube 42, S square 24.08, S to the power of 1, the answer is 0. S to the power of 0, the answer is 0. Next, S cube 0, S square 0, S to the power of 1 is 0. And lastly, S to the power of 0 is, the answer is 0. Conclusion. In conclusion, the project successfully demonstrated the application of theoretical control system principle in modeling, designing, and analyzing an electrical circuit. The derived mathematical model accurately reflected the system behavior, and the controller design met the specified performance criteria of 15% overshoot. Stability analysis further confirmed that the closed-loop system is stable and reliable. This assignment provided valuable hands-on experience in system design, simulation, and technical reporting, bridging the gap between learning and practical implementation.
That's all from us. Thank you.